Alright, so this video is all about electric fields, what exactly they are, how we define them, and what's going on in that. Alright, so we're going to just zoom in really quick on these two pictures of electric fields that are around what's called a point charge. So you'll notice that the electric field is drawn as a series of lines, and there are arrows to indicate the direction of the field. This is a hypothetical perhaps, but anyway, it's what's called a point charge. It's a charge that's just concentrated in a single region, a small region. So perhaps this might be the charge produced by a proton, or maybe it's the charge produced by a nucleus, or maybe it's just the charge produced by a small positively charged thing that's held in place in some apparatus. But in any case, this would be a small point charge, and then the field would be in equal directions all around it, because it's what's called a point charge. So the lines are equally spaced, which means that the electrical field is equally strong in all directions. If the lines were closer together or there were more of them, that would indicate that the field is stronger than this one, as shown. In any case, the arrows is the other thing we need to talk about. We'll quick look at a negatively charged point charge. All right, so that's negative. Again, it looks identical to the positive one in terms of the lines, but the arrows are opposite. So what's up with the arrows? Well, I'll just zoom it out so you can see. The field lines are drawn with the arrows pointing in the direction that an imaginary positive charge, would experience if it were placed in the field. So in the direction of the force. So if I stuck a random positively charged thing there in that electric field, it would experience a force away, because positive things repel each other. So this positive point charge would repel that positive charge. It would push it away. So the field lines are drawn in the direction that a positive charge would experience a force if it were placed into this electric field that's produced by that point charge. Same thing here. Arrows point in because a negative would attract a positive. So if we had a positive charge over there, bam, it would go in the direction of those arrows towards that negative. All right, so that's how you can tell which direction the arrows should point and why they're pointed the direction they're pointed. And here are some common field shapes for an electric field. We'll zoom in on this one. This is a Van de Graaff generator. A Van de Graaff generator is one of those things, oftentimes you've probably seen them, where they have a big metal sphere on top of this basically interesting looking plastic rod, and then there's probably a metal base down here that you can't see. All right, and this sphere on top. If you stick your hands on it, then your hair sticks out on end and all kinds of static electricity builds up on this sphere. So we've drawn it with positive charge on there. So this is similar to that positive point charge that we saw on the previous slide, but it's not a point charge because now it's a sphere. But otherwise it looks pretty similar. So the positive charges are going to spread themselves out over the sphere. Or more accurately, the electrons will spread themselves out over the sphere as much as possible, so that the positively charged regions are evenly spaced all over the surface of that sphere. Thus, the electric field should be basically even in all directions, which is shown by these blue arrows. Right. So that would be the electric field around a positively charged sphere, or a charged conducting sphere, as we have written down there. Let's see what it would look like if we put two point charges nearby to each other. So if we hypothetically imagine that we could keep these two charges in place but close to each other, then this is basically what the field would look like between them. You would have a strong interaction, a strong attractive force of these two fields, because of course the field is coming out from the positive into the negative. You can almost see them kind of like trying to pull each other together. But if they're held in place, they can't actually pull each other. But they would still be experiencing the force of trying to be attracted to each other and trying to go meet up. All right. So that's what you would see around 2 point charges that are nearby to each other. And then here is two different views of the electric field between two parallel plates that have opposite charge. All right. So here it shows the entire plates, and it shows that at the edges the field starts to bend a bit. So especially right near the edge, the field kind of bops out from the plates and goes around. But in the middle, the field lines should be basically straight up and down in between a parallel plate. So over here I've drawn, this would be the middle section of two parallel plates that have opposite charge. And of course the arrows go from plus to minus. So there would be this electric field generated in between these two plates. This is really important for some specific applications of electricity, including capacitors, which will be discussed later. In any case, that is what an electric field would look like between two parallel plates that have opposite charges. So just to summarize, electric fields are produced by any object that is electrically charged, and their shapes will vary based on the shape of the thing that's producing the charge. An electric field then is a region in which a charged object will experience a force. So any charged object will experience a force if it's brought into another electric field. Electric fields are generally produced by electrically charged objects, but they can also be produced in other ways, including by certain magnetic interactions, which we'll discuss later. And then the shape of the electric field depends on the shape of the object, and also any other nearby charges will also affect the shape of the field. So that's basically it for electric fields. That's what you need to know. So hope this video has been helpful. Thanks for watching, and we'll see you next time.